what am I supposed to do with my pressure lines? Because I need to draw my pressure lines, right? How many pressure lines do I have? How many pressure levels do I have? Two. Why two?
High pressure and low pressure.
High pressure to low pressure. So your colleague's saying I'm going to go from, well, high pressure is what? 2, 3, 1, 4. What is your high pressure? 2?
4 is low pressure.
4 is low pressure. Okay, so we're going to say, we're going to write it here on the side. This is low. What is 1? Low? Okay, low. Equal to or not to this one? Equal to. Now, that's assuming what? An ideal no pressure losses across that pool. Right? That is probably minimal. So we're going to assume, and we understand that 4 and 1 are somewhat equal, assuming minimal pressure losses. Now, later on, as you advance through the course, you're going to account for some of these losses. And you're going to have multiple pressure lines, and it's going to be fun. Okay, what about high pressure? Same principle. Now, think of what I said, constant combustion, constant pressure combustion process for gas turbine engines. And that's the same principle. So meaning that P here is high, P here is high, and they're both equal. So P2 is equal to P3. Now, does that make sense? Yes. If I go from a low pressure and I compress it through my compressor, and I'm burning and I'm expanding my, well, transferring heat and expanding my gas, then passing it through a turbine, which essentially what I took is heat input, some form of energy, transferred it into flow work, expanded by gas expanded, went through the turbine, produced what? Work. So that's the same principle. The pressure drop across there, given that this is a closed loop cycle, what's going to happen is the P3 has to go to P4, which P4 has to equalize. So does that make sense to people why we are going to do 2 lines, pressure lines right here? Right? P2 and P3 are the high pressure lines, and P1 and P4 are similar. Question?
Assuming ideal gas, and then we have a cooler and we have a combustion. So,
Well, it's heat exchangers. Yes?
yeah, so heat will grow our heat if we don't have a pressure change and we don't have a density change.
Very good.
What's the density?
Very good question. So, this is why I don't like to introduce this problem right now, because we need to go through reacting mixtures to understand and appreciate that while density is no longer constant, we took high-speed aero before this course for a reason. We can't assume density constant. So what your colleague is saying is, and it brings up a good point, we're going to write it out here. So, what is our ideal gas law, which is the first law that we have to actually list up? Rho RT, or you could take it as PV equal MRT, or you could say it's P equals RT, right? Specific volume, the pressure times specific volume is equal to RT. Makes sense to everybody? Forms of the ideal gas. We can never get this wrong. So density is equal to mass over volume, and density is equal to 1 over specific volume, and specific volume is equal to volume over mass. So you have all the equations here. No, so don't tell me they're not there. And we write them quite a bit. But what your colleague's saying is, if I am assuming constant pressure, right? I'm assuming between 2 and 3 the constant pressure. So if I write the ideal gas law, I'm going to say P2 is equal to rho 2 RT2, and P3 is equal to rho 3 RT3. Okay? But I'm saying they're equal. There is no pressure change. So rho 2 RT2, you could write this on the side. rho 3 R T3. Obviously, this is a universal gas constant, assuming there's no reactions that are going on, so my gas is not changing, so I can cancel the universal gas constant. So, in order for, if I'm adding heat and I'm expanding my flow, therefore my temperature is going to change. So, what your colleague brought up a good point is, well, what happens if my pressure is constant and my temperature is changing? What's going to happen? Density is going to change. Rho 2 is not equal to rho 3. Make sense? So that's sort of the pre-introductory to gas mixtures and reaction mixtures. So yes, density is going to change, and it changes quite a bit. Factor of 7 to 8 sometimes. And that's how you get actually expansion. You're converting the expanded gas into high velocity gas, and that's how you could get work. But anyway, back to our topic here. We're starting with station 1. All right, so what am I supposed to do? Station 1 is in advance of the compressor. If I'm assuming an isentropic process, so I'm going to hide this because we already have this. I just want to know what we're going to add. I want to keep this up. If I'm going an isentropic process through my compressor, what is that line? Straightforward. Yes, we just did examples like this, so it's straightforward. It goes through to S. But I actually have an actual process, which is an inefficient process, and I'm going to have to put more work in to get to the same result of the compressor getting to that pressure level. So think of, again, hand crank to actual. Okay, so now that I did that, so this is my actual. Obviously, this is like this. So I'm going from to actual, which is the entrance for the combustor. What happens after to actual? I said it's a constant pressure heat addition, right? So heat, what is that in the form of? So I'm going to have, by nature, an entropy change. So my 0.3 is going to be right here. Okay, now what? I'm getting into a turbine. The isentropic process through a turbine is what? Straight down. So this is for S. What about the actual process? Left or right? Okay, good now. All right, so I'm going to go this way, and this is the actual for actual. And that's essentially your brain cycle. So let's start to line up all the equations for these different processes. So we'll say, what do I have as inputs? I have P1, P2, T3, mass flow, the compressor efficiency, my turbine efficiency, my T1, CP, and gamma. These are your input control variables, and the outputs are primarily, what I'm interested in is workout, which you can translate into thrust, and thermal efficiency of my overall system. So let's revisit some of these terms. P1, well, if I'm working with a propulsion system, I know my ambient condition pressures. So this is an input that you already know, a known value. All right, so I know this. I know P1. P2, well, how am I deciding P2? You're the designer of this propulsion system. You're saying I need to compress that gas up to this pressure in order to burn at this rate and expand it and produce this much thrust. So you dictate P2 as a designer. So I am putting this in, and I know it. T3 is what you're deciding how much what. How do I decide T3? coming in. So you're a designer again. You're dictating that value. So you already know this because you're changing it. Remember, you're constructing a model. So essentially, if you say, well, how am I supposed to do this? I don't know what I need to get at. Well, let's say the Air Force comes back to you and says, I need this much thrust. So you come up with an indicated guess for these values, but you have a model based on the equations, and you try, for example, 2,000 Kelvin, and while 2,000 Kelvin gets you half the thrust that is required by the Air Force, then you go back and readjust it again. But you already have the model equations. Hence, that's what you colleagues were mentioning about using MATLAB. But you can do this in Excel. You don't need MATLAB for this course. But it's very crucial to learn it. Okay, so these are inputs you're deciding. Mass flow. Well, how much mass flow through my system do I want? How do I dictate mass flow? How can you dictate mass flow? Area. Very good. It's m dot rho AV. Area. Size of the engine. And you're going to do this later on. So you're still the deciding factor of this. Compressor efficiency, well, that's a byproduct of your design primarily. So depending on how much stages, so these are different stages that go on inside. You might have a lot of stages, minimal stages, and that translates into your compressor efficiency, your blade design, and we'll talk about them later on, but you spend quite a bit tailoring those efficiencies, but you're still the lead designer and deciding these factors. So this is an input that you already know. I'm going to make my compressor 75% efficiency because I have learned in the past by having 3 to 4 stages, that's what gets me to 70 to 75% efficiency. So I'm going to take it at 75% efficiency. And the same thing with the turbine. The turbine is actually higher, it's in the 80s. Okay, so, and you're going to interact with these values in the course. T1, well, I don't control the ambient temperature, so, or the gas I'm going to put in there, so that's known, but I'm putting it in. CP, well, I know the gas that I'm putting, I know my temperature level, so I can compute CP accordingly and get CP based on my temperature range. And the same thing with gamma. So these are all inputs that you control, and it's known values. So I'm going to say known values. What do I don't know? Work out, which is essentially a thrust, and the overall efficiency of the system itself. So, and that's what we're going to characterize. So, based on this, let's start with each component. Well, let's outline first our conservation equations, conservation of mass. Well, this is a closed loop cycle, and there's only one path through my mass. So, and it's steady state. So what do I get? I get m dot 1 is equal to m dot 2 is equal to m dot 3 is equal to m dot 4. Straightforward. Mass is equals to m dot. That's it. Now, compressor-wise, or now I'll go and say compressor. Let's apply conservation of energy. What's conservation of energy? The rate of change of energy over my control volume over dt is equal to Q in plus work in plus the summation of m dot in, h in, minus the summation of out and enthalpy out. Okay, so this was my conservation of energy equation, which we drew last ago. I assume steady state. So what happens to this term? Cancels out. Is this one dimensional? Yes. So this cancels out. Steady state equals 0. Through my compressor, do I have heat transfer across there?
No.
Why?
You could do that.
Very good.
All right, so I only have work. Well, I do have work because I'm putting work into my compressor. And I do have enthalpy changes. Now, I can simplify this equation because m dot in versus m dot out is what? They're equal because I got it from conservation of mass. It really doesn't matter. So I could say work of the compressor, which is in dot rate, m dot is equal to, what is enthalpy in versus enthalpy out?
HM minus HM.
Which enthalpies?
It's H1 minus H2.
Okay, so that is correct. Now, should we do H1 minus H2A or should we do H2A minus H1? So it's correct.
H2A minus H1.
But if we say H1, so you don't have to write this down, but I want to clarify it or write it on the side. H1 minus H2A. What am I going to get?
Negative word.
A negative. So what that tells me about work? It's work in. So as long as you're familiar with, so you can keep it that way, but just follow the same path of how you went. You went from here to here. So the fact that you're going to get a negative value here just tells you that it's work in. So, and hence I was covering this, right? But if I put this, right, that tells me is just positive work that I already know I'm classifying as work in. But what your colleague mentioned is very valid, and what I'm going to say is yes, that is correct. But you could say it's just keep in mind this is work in. But essentially, you want to, if it depends on your path in general. If you start to get confused with the signs, just follow the same path and you'll be fine. If you do the same process, so if you follow the same process through the turbine, you're going to get the opposite value and things are going to check out. And everything's great in the world anyway. But the important thing is understand it